Welcome back, Math Apps peeps. I'm going to finish up. This is day 12. We were able to do the second example with method B, but I'm also going to show with method A in case you like that method better. So remember, with method A, we're pretty much treating the top as its own problem and the bottom as its own problem. So I'm going to take the top here, 1 over x minus 4. And I need to have common denominators when I add fractions. So I'm going to multiply this term by x minus 4 over x minus 4, giving us x minus 4 over x minus 4 plus 1 over x minus 4. Now, since I have common denominators, I can add them together, which leaves me with x minus 3 over x minus 4. Okay, that's the entire top now. And now I can move to the bottom. With the bottom, it's 1 minus 1 over x plus 2. In order to add fractions, I need that common denominator. So x plus 2 over x plus 2. Now our fraction becomes x plus 2 over x plus 2 minus 1 over x plus 2. Since I have these common denominators, I can now combine the numerator. So x plus 2 minus 1 is x plus 1 over that denominator. I have the top and the bottom. Let's put it now back into the fraction. I'm going to shrink this a little bit. So the top, and here's the bottom. Instead of dividing fractions, you can also multiply reciprocals. That means take your numerator and multiply it by the reciprocal of the denominator. So x plus 2 goes on top, x plus 1 goes on bottom. You take the reciprocal of the denominator. Why did I do this? Because now when I'm multiplying, let's change my color here, I get just two fractions. No fractions in a fraction, just having your binomials. So I have to FOIL the top, x squared minus x minus 6. And then I FOIL the bottom, x squared minus 3x minus 4. Realizing that is the same thing as those binomials actually multiply together. So I could leave it in either form. It's probably easier to leave it in this factored form here so you can see if anything cancels. But there is method A, and as you can see, it matches method B. Either way, I have no preference, whatever speaks to you. If I have a problem like number 3, first thing you want to do is you can't have negative exponents. So let's simplify that. Right off the bat, I'm going to have b over a minus a over b. These negative exponents I put in their own denominator. All over a squared plus b squared. Treating this like a method A or method B, it's up to you. Doing method B, because that's what majority of us liked in class, means we have to find the least common denominator with all of our little denominators. Well, that's going to be, I'm so sorry, that's going to be a B, because this denominator is A, this one's B, the least common denominator would be AB, which means I'm going to multiply every single term by AB. Every single term by AB. When I do so, AB times B over A, well, the A's will cancel, leaving me with just a B squared. AB times negative AB, well, the B's will cancel, and left with negative A squared. On the bottom, AB times A squared is A cubed B plus an AB cubed. Trying to simplify, notice the top is difference of perfect squares. And the bottom, I can do a GCF. So this one's going to be difference of perfect squares. You always have to keep going. And this one will be a GCF. So you'll get b minus a on the top, b plus a on the top. On the bottom, you can take out a common a and b, leaving you with a squared plus a b squared. You cannot simplify anymore. There's no such thing as a sum of perfect squares. Nothing cancels, so you're done here. And that's the rest of day 12. If you need any help, please ask in class.